In this short video, I'm going to talk about the solution of the bonus problem number 1. We have been asked to find the resultant force of water on the plates AB on the photo that you can see on this slide. Note that the plate is 4 feet wide into the paper, and that water exerts pressure on the plate, and as a result of that force, so we have been asked to find the resultant force. In this slide, I'm going to show you how to find horizontal force, and in the next slide, I'll talk about vertical force. In order to find horizontal force, the first step is to find out the vertical projection of plate AB, which would be something like this. And again, it is 4 feet wide into the paper, so it would be a rectangle that is 4 feet wide and 6 feet wide, because this is 6 feet. Perfect. Now, if I ask you what would be the pressure over here, you would tell me that it would be 0, because that's on the surface of the water, and pressure at the bottom over here can be shown by this arrow. So the arrow shows the magnitude of pressure. Now, pressure distribution can be drawn at like this. It is a triangular pressure distribution, and this point would be the point that FH exerts, and FH is our horizontal force. Okay, so in order to find F sub H, you have different methods. One method would be using the very familiar equation, which is specific weight of water times h bar times area of vertically projected area. Another method is geometrical method. So in geometrical method, FH is equal to volume of pressure distribution on the vertically projected area. So I'm going to write it down. Volume of pressure distribution on the vertically projected area. So to calculate that volume, first we need to calculate the area of the triangle pressure distribution. Basically, we need to calculate the base of the triangle, and the base of triangle represents pressure at that point, and pressure at that point would be gamma of W times 6 feet. All right, now I can write FH to be equal to volume, which is area of triangle, times how wide it is, which is 4 feet. Now I'm going to replace the area. The area of triangle would be half times the base is gamma W times 6 feet. And the height of the triangle is also 6 feet times 4 feet. So if you calculate this using Excel or using your calculator, horizontal force will be 4.493, and the units for that would be kilopounds force, or the abbreviation for that is KIP. All right, so this is the horizontal force on this circular, or I should say semicircular plate. Now, next slide, I'm going to talk about vertical force. All right, now we are going to calculate vertical force. And to do that, what I'm going to do is simply name some of the critical points that I am going to work with. So this point, I'm going to call this C. Okay, now if I ask you what would be the vertical force, you would tell me that this gate is consisted of two parts, part AC and part CB. So the characteristics of these two parts are different. Specifically, when we are talking about part AC, you can see that water or fluid is above part AC. So if I want to sketch that, it would be something like this. So the vertical force on part AC is in this direction, right? How about part CB though? Let me remove part AC from here. Okay, so now if I ask you what would be the forces on part CB, you would tell me it would be the weight of the imaginary fluid on top of CB. So the weight of imaginary fluid would be volume of this area that I'm going over times specific weight of water. Okay, so the direction of this would be up, right? So just to recap everything, I'm going to say force acting on CB. I'm going to remove this from here and draw it over here. It will look like this. Okay, so if this point is point B, this point is point A, I'm going to call this point D, and this point would be point C. So the direction of this force would be up because fluid is below CB. Now, also I can write force acting on AC, and that would be simply something like this. Now, naming the points, this is A, this is D, and this is C, right? So if I want to show you, D would be over here. There we go. And the direction of this force would be down in this direction. Okay, so instead of calculating both of these forces, because already polygon ABCD has this part in it, look at it. I'm going to actually show it to you. So these forces actually cancel each other out, right? So the only thing that I need to calculate is this part. It's the semicircular one. This would be B, this point would be C, and this point would be A. So if I calculate the volume of this times the specific weight of water, that would be the force acting on plate AB, right? To calculate that, it's pretty easy. You just need to write F vertical is equal to gamma of W times volume of BCAB. BCAB. So the vertical force would be equal to 62.4 because it is in the US customary units, and then times area of the semicircular region would be half of area of the circle, so half of area of the circle times the width of the plate, which is 4 feet, so times 4 feet, and as a result of that, the amount of vertical force is equal to 3.529 kilopounds force, or kip. All right, so the point over here is that whenever you have a situation in which there are some water on top of your plate and there are some water below the plate, you just need to calculate the difference between the two and calculate the volume and the weight of the water in between the two, okay? Like in this situation, we knew that already this force is canceled by this. So what I did, I simply took out the area ACD out of ABCD and calculated the volume of the semicircular region for here. Okay, very simple.